Greetings and salutations once again. Morning, evening, mid-afternoon, whatever time it is for you. I told you that I was going to use the slides from this other text, but this particular chapter, I think the slides from your text are pretty good, and I like their descriptions. I want to simplify some things a little bit, that they get into a little bit too much detail that you don't really need to know. So this will be chapter 2. We're talking about atoms, molecules, their characteristics, how they work together, what are the molecular forces that make physiology work. And so, of course, we're focusing on physiologic things. We're not so concerned with, other chemistry reactions. This is not a chemistry class. But we do have to focus on the chemistry that applies to human bodies, and that is physiology. So here's the here's the slides that are straight out of your book. These pictures are straight out of your book. The descriptions are straight out of your book. So let's look at this. Chapter 2. Yep. All right. So we have to talk about, we hinted at this in the first slide. I'm sorry, the first slideshow. We hinted that we were going to talk about atoms and elements, and so in order to understand that, you have to understand there are 3 subatomic particles: an electron, a proton, and a neutron, and those combine together in various ways to make atoms. Something that I will tell you about an atom is electrically neutral. What does that mean? A proton has a positive charge. An electron has a negative charge. Electrons are flying around protons in the nucleus. The protons, and there's another thing in there, in the nucleus of an atom. And flying around the outside, kind of like a planet around the sun, is an electron or several electrons. Protons have a positive 1 charge. Electrons have a negative 1 charge. An atom needs to balance out negatives and positives. That means an atom has the same number of protons in the nucleus as it has electrons flying around the outside of it. That's an atom. If those things are not balanced, if this atom has 1 less electron than it would need to be neutral, or 1 more electron than it would need to be neutral, it is no longer called an atom. It is called an ion. Now you might say, well, what the heck? It's still an ion, still an atom. Yes, but specifically we're speaking of an atom has no charge to it. An ion does. And they behave differently. And I'm going to show you that in a moment. So, to get back to this slide, you can see there are 3 forms of matter. You're familiar with these forms of matter, right? They're solid. Touch your skin, hit yourself. Solid. Solid. Liquid, right? You're full of blood. You have other liquids inside you. And gas. We in a physiologic sense, we deal with all 3 of these things: solids, liquids, and gases. And your body, your anatomy and your physiology is designed and set up to be able to use and interact with these 3 forms of matter. So an atom is the smallest particle exhibiting the chemical properties of an element. It's a little bit of a circular definition, but an atom is electrically neutral and has the properties of the rest of that particular element. So there's 92 naturally occurring elements to make up matter. Chemically, these are organized into a table. So this table, this thing called the periodic table of the elements. You don't have to memorize any of this stuff. The colors of the elements that you see there are related to the most common, by far and away the most common atoms that are found in humans or any mammalian life form. These are the ones, these colored ones. I'm going to show you on a table. You don't have to know where they are. They are arranged, the periodic table of elements is arranged by what's known as the atomic number of that element. So you see up here hydrogen. Hydrogen's number 1. It's element number 1. Then you go way over there. We're going to talk about electronegativity. Don't worry about that yet. Way over here is element number 2. That's called helium. Then you come back to the other side. Element number 3 is lithium. And then you have beryllium. And then you have boron, carbon, nitrogen, oxygen. Aha, these are very, very important life forms. Our life forms. And then sodium, magnesium. Now, this you can figure out, right? H, hydrogen. Makes sense. C, carbon. Got it. N, nitrogen. Beauty. O, guess what? Oxygen. Yes, you guessed it right. Now we get over here. Na. That would be what? Nearby? No. Sodium. Na is sodium. What? Sodium? Yes. Na stands for the element sodium. Magnesium, makes sense. Phosphorus, sulfur, chlorine, beauty. Got them. K. Huh? Potassium. Yeah, I know. Potassium. It's a Latin thing. Fortunately, Ca. Calcium, as you would expect. And then here's the last of the weirdos. Fe. Iron. Yeah. So, now, here's the most common again. Arranged now by how much they contribute to your body weight. The weight of your body is predominantly oxygen. But not oxygen the way you think of it. Not oxygen like out in the atmosphere. It's bound up with other atoms to make molecules. And those molecules, most of those molecules have oxygen in there somewhere. And then by decreasing percent, carbon, hydrogen, nitrogen, calcium, phosphorus, and so on, all the way through these, and the percent that they make up of your body weight. Now, just because iron makes up 0.006% of your body weight does not make it not important. It's extraordinarily important to have even that little bit of iron in your body. Incredibly important. So you shouldn't rank these or think that these are ranked by importance. That's not it at all. They're just ranked by how much is in you. So here we go. Atoms. Atoms, 3 subatomic particles. I mentioned if you're taking a physics class, you'll laugh at this. Don't worry about it. You have 3 of them. Neutrons, protons, electrons. Okay? Neutrons and protons are found inside the nucleus. They're smushed together. They're all jam-packed together in the nucleus. Electrons are flying around the outside. An atom, by definition, must be electrically neutral, as I've already said. So a proton has a positive charge of +1, and an electron has a negative charge of -1. You must balance out. So an atom has equal number of protons to electrons. Now neutrons, that's kind of the variable. You can have more neutrons than protons, or fewer neutrons than protons, or no neutrons. If you're hydrogen, you have no neutrons. Now, the other characteristic about atoms that is important to know, as I said, this is not a chemistry class, so we're not gonna get deep into the chemistry of this. But protons have a weight. They weigh something. I know, not a lot. I mean, atoms are very, very tiny, and protons are even tinier, of course. They don't weigh much. But we say that a proton has a mass. A mass is, for all intents and purposes, you can think of mass as weight. Again, if you're taking a physics class, mass and weight are not the same thing. However, for our purposes, they are. We measure the weight of a proton in what's called an atomic mass unit. Don't worry about what that is. A proton weighs 1 AMU, 1 atomic mass unit. Likewise, a neutron that is also in the nucleus with the proton has the same weight. It weighs the same thing. They're not precisely the same. Again, if you're taking physics, they're not exactly the same. For our purposes, they are. That's all we really care about. Again, a neutron has 1 atomic mass unit. A proton has 1 atomic mass unit. So they weigh the same. A proton has a charge of +1, but a neutron, as you might expect, has no charge. Now electrons are very tiny, very small, and we essentially consider them to have no weight. That is not technically true. If you're taking a physics class, you're going to see, yes, they do weigh something. They just don't weigh very much. So 1/1800th the mass of a proton or neutron. So when we're weighing an atom, the electrons of that atom don't add to the weight. The neutrons and the protons are the things that weigh something. So when we talk about an atomic mass, or how much does an atom weigh, you add up the neutrons and the protons. That's how much it weighs. However, when we're ordering it according to the periodic table, we order it according to how many protons there are in that nucleus. That's called its atomic number. So if it has 1 proton, which hydrogen does, 1 proton, it's element number 1. If it has 2 protons, which helium does, we say it has an atomic number of 2, and so on. You've already seen each element has its own unique chemical symbol. Some of them make sense. I've shown you some of them don't make sense. But that's how they are. When we draw them out, when we draw out these molecules, you're going to see these letters. Carbon's attached to a hydrogen, is attached to an oxygen. You're going to see a C and an O and an H. And that's what they refer to. As I said in the last slide, the atomic number is how many protons you have in that atom. So we line them up on the periodic table based on how many protons they have in the nucleus. What does that tell you? That tells you if there are 6 protons in the nucleus, that atom has 6 electrons flying around it, electrically neutral. Now, the atomic mass is, remember I told you that protons and neutrons weigh something, but electrons don't weigh anything. They're so light, we don't really count them in. So if they have a certain number of protons and a certain number of neutrons, so if it has 6 protons and 6 neutrons, it weighs 12. 12 what? 12 atomic mass units. Don't worry about what the units are. It weighs 12. So we say its atomic number is 6. And its atomic mass is 12. That's carbon. I just told you what carbon is. And we're going to talk about some variations on a theme here. So here it is in summary, right? The proton number, the number of protons in the nucleus, is the atomic number. Always. What that tells you is that same atom has the same number of electrons flying around the outside. In the same nucleus, the neutron number is protons plus neutrons equal the atomic mass. That's the total weight. Now what this slide is telling you, it doesn't matter so much to me that you understand this slide as much, but I want to tell you what it says. What it's saying here is, if you add the protons and neutrons together, you get an atomic mass. Yep. And if I took that atomic mass and I subtracted the atomic number, which is what again? That's the number of protons. So if I took the whole atomic mass of the thing and I took away the atomic number, that would tell me how many neutrons there were in the nucleus. So they give you the example of sodium. Remember, sodium's a weird one here, Na. And they say, well, sodium, the element sodium, or an atom of sodium, has 23. Its atomic mass is 23. What do we know? That is that's protons plus neutrons. So it weighs 23 atomic mass units. But I also know that the atomic number is 11. Well, the atomic number is the same as the number of protons. So if I take its atomic mass and I subtract the number of protons, which is the atomic number, I get 12. What does that tell me? That tells me how many neutrons are in the nucleus. So you can see in this case, it's going to have 11 protons and 12 neutrons. So neutrons and protons don't have to be the same. And again, electron number equals proton number. I've told you that several times. Okay, now, the next thing you have to understand, why do you have to understand this? Because you have to understand how these atoms are built, and then you have to understand how the atoms interact with other atoms. That's where we're going to get molecules. That's where we're going to talk about physiology at that point. Now, I've told you that the electrons are flying around the outside. Well, they're not flying randomly around the outside. They're flying around the outside in very specific areas around the nucleus. These areas that they fly around in are called shells. The shells can hold only a certain number of electrons. And it depends on which shell you're talking about. And these shells, you can think of them as planets orbiting the sun. It's a little bit different than that, but let's think of it. So the innermost shell of our solar system would be Mercury, would be flying around the sun. So we would call that the innermost shell. Well, that's the same with electrons going around the nucleus. The innermost shell is the one close to the nucleus, relatively close to the nucleus. That particular shell can hold two and only 2 electrons. That's it. That very first shell holds 2 electrons. After that, if you're gonna jam on some more electrons, if you're gonna make the same number of electrons as you have protons, because you have to do that, if you're gonna do that, then you would have to fit the next electrons in the next outer shell, the next bigger shell. And these shells get bigger, and they get bigger, and they get bigger, and they get bigger. That next shell can hold 8 electrons. It doesn't have to. When I say that a shell can hold a certain number of electrons, it doesn't have to hold that many electrons, but it can. It can go up to a maximum number of electrons. So, as an example, I'm going to show you their example in a moment, but as an example, let's take hydrogen. Hydrogen is number 1, right? Number 1 tells you it has 1 proton. I can also tell you that hydrogen, on the periodic table, normal hydrogen has 1 proton and no neutrons. So to balance out the electrical forces, you would say, okay, I got to have 1 electron flying around that 1 proton. Yes, that's right. And that 1 electron would be in that first shell around the proton. Now, I said that shell could have 2. It can hold 2. Yeah, but hydrogen doesn't have 2 out there. Okay, so it's got a spot for another electron. It could have another electron. But then it wouldn't be electrically neutral anymore. Now, these things do exist. But if you're saying an atom of hydrogen, an atom by definition is electrically neutral, so you have to have 1 proton and 1 electron, and that's it for hydrogen. If you changed the number of electrons flying around it, it's no longer a hydrogen atom. It would be a hydrogen ion. That particular one doesn't exist, but that doesn't matter, just for example. So, you think of these things as shells. The first one holds 2 electrons. The next one can hold 8 electrons. It turns out the one shell above that can also hold 8 electrons. Can, but doesn't have to. All right. Now, an isotope, or maybe you've heard of isotopes, because isotopes are used in medical testing quite a lot, actually. An isotope, and this is the reason that they're used, is because isotopes are what we refer to as radioactive. That means they give off certain waves of the electromagnetic spectrum. We won't get into that in too much detail. But an isotope gives these radioactive waves off, and they can be detected by special meters, special test protocols. And so they can be seen. You can see the results of these, where these isotopes go. We're going to get into an example in a moment. Now, iodine is a classic example of, if you suspect that somebody has a thyroid problem, you can check it, because iodine is used by the thyroid gland in the production of thyroid hormone. There is no other hormone, there's no other molecule in your body that uses iodine. And so iodine is beautiful to use to look at thyroid or suspected thyroid problems. It's beautiful because it's radioactive. It's taken up only by the thyroid, and then we can look at that. We can measure it with a measuring device, a tool, a machine, and we can see, yes, look at this, there's a problem. Either it took up too much iodine or it didn't take up any iodine. Either way, that's a problem with the thyroid. But an isotope, what's an isotope? An isotope is, an isotope of iodine would have more neutrons in its nucleus than you would normally find with iodine. They give you the example here of carbon. That's another great example. So carbon-12, well, we call it carbon-12 because that's normal carbon. When you think of carbon, that carbon has 6 neutrons in its nucleus. What does that mean? It has 6 electrons flying around the outside of it. Okay, that's an atom of carbon. Great. How many neutrons does it have? Well, normally, normal carbon, and what we would call carbon-12, has 6 protons and 6 neutrons and 6 electrons. There you go. But there are other isotopes of carbon that have more neutrons in the nucleus. So carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. Yep, you can do that. It's not very common. These are very, very uncommon. But they're common enough that we can measure these things. We can measure the difference between carbon-13 and carbon-12. That's called carbon dating. We can actually measure the difference. It takes a long, long time for carbon-13 to lose that extra neutron to become carbon-12. But as it does that, we call that radioactivity. And we can measure that stuff. All right, so an isotope, so a radioisotope contains excess neutrons, as I've just told you. We just saw that with carbon-12. Those excess neutrons are unstable. Now, we won't get into the physics of the whole thing. It doesn't matter. Just understand, if it's got more neutrons than it ought to have, it's unstable. Unstable means it's radioactive. So it loses nuclear components in the form of high energy radiation, as I said, along the electromagnetic spectrum. These things don't matter. Alpha particles, beta, gamma rays, doesn't matter for us. We don't care. All it is saying that isotope is giving off radioactivity, not dangerous radioactivity. Carbon-13 certainly isn't going to kill you because it's radioactive. It's so incredibly small on the radioactive scale, you wouldn't even know it. However, radioactive uranium or radioactive plutonium, yeah, those can be quite deadly. An isotope has what we call a half-life. I'm actually going to go through this slide very quickly. This is not an important topic, but a half-life is, if there's a certain amount of radioactivity that atom has. How long does it take to lose half of that radioactivity? That's what a half-life is. Some isotopes have a very, very short half-life, on the order of milliseconds. Some carbon-13 has a half-life of thousands of years. So it all depends. Various isotopes have different half-lives. Now, this is an important concept. Biologic half-life. Your body makes molecules, right? And those molecules float around your body, but they don't float around forever, right? You make insulin, but that insulin doesn't float around you forever. The insulin is degraded at a certain point in time, and it takes a certain amount of time for that insulin, for half of that insulin, half of the concentration of insulin to go away. And then it takes the same amount of time for that next half to go away, and the same amount of time for the next half to go away. And eventually it has no physiologic relevance to you at all. So you have to make more insulin. That's why you constantly make these things, because they get broken down and they get reabsorbed by your body, or they get eliminated by your body. And that's referred to as a biologic half-time. That's why or half-life. That's why you have to constantly make more of this stuff. Okay, so here's the medical view, right? Medical imaging of the thyroid gland using iodine radioisotopes. And I've already mentioned this, right? So radioisotopes, you're given iodine either in an injection or you swallow it. Iodine is taken up by your thyroid gland. Your thyroid gland in darker areas where less radioactivity iodine is taken up can help you locate a nodule inside the thyroid gland. There's all kinds of ways that radioactive isotopes are used in medicine. All right, now, I've told you already, an atom, by definition, has a certain number of protons. They have a positive charge. Around electrons, negative charge, they must be equal. But a lot of times in physiology, we're dealing with ions, not necessarily atoms. Why? We're going to talk about that in a minute. What does it mean to be an ion? An ion either has a positive or a negative charge. That means you've taken whatever atom it was, and you either added electrons to it and made it a negative thing, have a negative charge, or you took electrons away from it and you made it have a positive charge. That's an ion. An ion has a positive or negative charge. You produce an ion from either losing or gaining electrons. You could gain 1 electron, you got a negative 1 charge. You could gain 2 electrons, you have a negative 2 charge. Or you could lose 1 electron, you have a positive 1. You could lose 2 electrons, you have a positive 2 charge. It's just because those charges don't balance anymore. Right, so here you go. The example, K+. Potassium. Huh? Yes, this is potassium. Potassium plus, the ion, is used in sports drinks to help replace potassium lost in sweat. Potassium in a large dose is used for lethal injections because potassium, high-dose potassium in your bloodstream is very bad for your heart. And it interrupts the rhythmicity of a heartbeat. And so it makes your heart stop beating. That has to be a very high dose of potassium. But it is true. It is used. It is one of the components of a lethal injection, which is sad, but true. Now, losing electrons helps to stabilize an atom. Now, stability simply means those outer rings where the electrons are found. I told you that the inner one can have 2 electrons. The next ring out can have 8 electrons. And in a sense, if you want to think of it, if you want to anthropomorphize this atom, it would like to have 8 electrons in that outer ring if it could. So if an element, or if an atom, an element, has 7 electrons in that outer ring, it would like to have 1 more. On the other hand, the other side of that equation is if you have only 1 electron in one of those outer rings, that element would like to get rid of that electron. That's called enhancing the stability of that atom. It also makes them have a charge. So if the one with 7 electrons gained 1 electron, it would have a negative charge. It would have 1 more electron than it would have protons. And the other side of the coin, you have sodium. Sodium. I'm getting to the actual elements. You have this element, sodium we'll say, that has an extra electron, one electron in its outermost ring, and it would like to give it up. Well, I've just described to you sodium and chloride. So sodium would like to lose an electron, so chloride likes to gain an electron. That enhances the stability of that element. But now they're not atoms anymore, atoms in the specific sense. They are now called ions. Chloride has a negative charge, sodium has a positive charge. Hey, guess what? Opposites attract. So now they're attracted to each other. So they are, we call that a bond. And that bond is called an ionic bond. Makes sense. Now, I want to show you something. I want to show you a video. Well, let me describe this. Don't worry about the octet rule. All we're doing there is we're taking the extra electron from sodium and sticking it into the outer part of chloride, which would like that electron. That makes them both happier, if you want to anthropomorphize. But it makes chloride negative, makes sodium positive. Now, if something has a positive charge, sodium gives up an electron, has a positive charge. That's called a cation. The way I remember this, I mention it this way. I do like cats. I don't own any cats, but I like cats, right? So I always feel like I like cats. I feel favorable about cats. I feel very positive about cats. So a cat ion has a positive charge. If it has a positive charge, that means it's missing an electron to balance out its electric forces. The opposite thing is called an anion. An anion is an ion with a negative charge. Now, there you go. Gaining electrons forms anions. That makes them negative. So chlorine, which is electrically neutral, gains an electron from sodium, which wants to give it up, and it becomes an anion. It becomes negatively charged. That at the same time, sodium has a positive charge. Now it becomes a cation. They are now attracted to each other, and they create an ionic bond between the two of them. Ionic bonds are all over your body, everywhere. Now, when an anion and a cation get together, they usually form what we call salts. Now salts, they form salts when there's no water around, when they're not dissolved in anything. So of course you have table salt, sodium chloride. It's on your table. You have table salt. But if you were to dissolve that in water, we wouldn't call that table salt anymore. We wouldn't call it a salt. We might call it a salty solution. This is important. This concept is going to become important when we talk about water and what water does to these, what water does and the influence that water has on these ions and the special properties that water has, and why water is so important in your body. We have a hard time imagining life. Certainly life on Earth could not occur without water. So that's why when we look at these planets around other suns, we're looking for water. If we see excuse me, if we see a planet or even some of the moons of Jupiter, they have water on them. We're very curious now. We're like, wow, water is such an important thing to life here. And it's because of the properties of water. And partially the properties of water help to dissolve these salts and allow these salts to influence physiology. Now I want to show you something. Let me go one more slide. Oops. Yeah, okay, so this is the picture form of an ionic bond, a formation of an ionic bond. So here's sodium. Sodium, I told you already, it has that one extra electron floating around. One extra meaning it only has one electron in that outermost shell. It would like to have 8, or it could have 8 out there, but it only has 1. So sodium is like, I'm not really too fond of that electron that's way out there. Chlorine, on the other hand, already has 7 in that same outer shell. And it says, boy, I sure would like to put 8 in there. Sodium says, hey, I can help you out. So that electron is transferred, is literally transferred over. But now we have sodium ion and a chloride ion. And remember, because sodium's positive, it's a cation, and chloride is negative, and so it's an anion. And these things are attracted to each other. And when you put them together and you take all the water away, they form salt. And this is what salt, your table salt, that's what it looks like on a molecular level. All right, now I'm going to show you something. Whoopsie, gotta go back. Going too far forward. All right, so I want to show you something. Oh dear, I do want to show you something. All right, I mentioned to you that I wanted to show you something. Well, this is the thing I want to show you. What these people are doing, you know, this is fun to do. However, it is dangerous. What these people are doing is they are taking solid sodium, and solid sodium looks like this. It looks like a silver metal, and this guy will have it in his hand. The solid sodium, he's going to throw it in the water. Now, remember, solid sodium is in its elemental form. That means it has that extra electron, one electron in that outer shell, just flying around. Sodium would like to get rid of it, but when it's in its solid form, it can't get rid of it, so it just stays there, right? Well, when this guy throws it in the water, it can get rid of that extra outer electron, and it can get rid of it to the water itself, but it gets rid of it very, very rapidly and very aggressively. And here's what happens. So this is a little bit more than a minute long. I'm just going to play it for you and let it run, and you get to take a look at this.
Alright, I'm gonna just keep throwing it.
Oh! Explosion!
I need slow motion. Hold on.
Wait.
We are recording.
Wait.
Hold on. Wait. Can I throw it far or no? This is sodium. That's fine. Go that way?
Oh no! Yeah! Wait, it's like a volcano. What is?
It's pretty impressive.
It's sodium.
Okay. Yeah, so that's sodium. Yes. All right, we got to get back to it now. There we go. Right, so that's what happens. Sodium is losing that electron so aggressively, it's explosive. Now, table salt is not explosive. You could go ahead and do that with table salt, and it will just simply dissolve in the water. The point to me showing you this is that the characteristics of atoms changes when they become ions. Okay, so you don't explode. You're full of sodium, but you don't explode. That's because it's an ion. not the solid. So I like that video. They're kind of crazy. It's sort of fun, but I wouldn't go around throwing sodium at people. That's not good for them. All right, so this is an example of one kind of bond that atoms can form together, an ionic bond. The next kind of bond, ionic bonds are the electron is given from one atom to the other atom. It's given up completely. They don't share it. One atom gives up an electron to another atom. That's it. It's only because they are positive and negative now that they're attracted to each other, and we call that an ionic bond. The next kind of bond that we can get is what's called a covalent bond. Covalent is now these electrons are sharing. Instead of one giving up, these two atoms or more share electrons. And that is referred to as a covalent bond. Now they could share a pair of electrons. One pair of electrons shared between two atoms is called a covalent bond. That's termed a single bond. But sometimes some elements can share two pairs of electrons. If they share two pair, that is a double covalent bond. Or if they share three pair, you can have a triple covalent bond. Now that's as high as the bonds go. You can only get up to triple covalent bonds. But they're sharing. Right, so atoms are shared. Both atoms require electrons. So these are the elements that in that outer shell they have maybe 2 or 3 or 4 electrons, or well, it's 4 to 7 electrons in the outer shell. 7 would be kind of pushing it, but you'll see that with atoms that have that they would do better. Instead of giving up an electron, sharing the electrons would make them happier. That's kind of the point that I was trying to get at. Was you think about it as they want to be happy. How are they going to be happy? Well, if they could fill up or get close to filling up the outermost shell, they would be happier. They can do that by sharing in the covalent bonds. So most of the time you're going to see covalent bonds in hydrogen, oxygen, nitrogen, carbon. Those are the big covalent bonders. Now, I just mentioned that you can share one pair of electrons. That is called a single covalent bond. You can share 2 pair of electrons. That's a double bond, or triple bonds. Now, it can share, like carbon is a good example of an atom that can share 4 pair of electrons with 4 different things. So like CH4 is methane. That is carbon with 4 hydrogens attached to it. And it is sharing a single pair of electrons with each one of those hydrogens. So it has 4 covalent bonds with the hydrogens that are around it, sharing those bonds, called covalent bonds. Covalent bonds are usually quite strong, hard to break, but in physiology they are broken for specific reasons, and that's why you have to understand the nature of this. Right, so this is just what I just said. Right? If you share 1 pair of electrons, you have a single covalent. If you share 2 pair of electrons, you have a double covalent. If you share 3 pair of electrons, and I mean between 2 atoms. So if a nitrogen and a nitrogen share one nitrogen atom, if they share 3 pair of electrons between those 2 atoms, we call that a triple covalent bond. But just as easily, this one nitrogen could share a single covalent bond with a hydrogen over here, and a hydrogen over there, and a hydrogen over here. So it would have 3 single covalent bonds. Some atoms can do both. Some prefer one or the other. And here's the graphical representation. This is one of the things I really like about your book. Is these pictures are great. right? Here's a hydrogen, here's a hydrogen. Remember I said a hydrogen has one electron around the outside. Well, another hydrogen has another electron around the outside. That shell would like to have two, or could have two. It would be happiest if it had two. So it finds another hydrogen and it says, hey, let's share. And it shares these electrons. And so each one of these hydrogens considers it its electron. And so that shell has two electrons and this shell has two electrons, and they say, oh, we're happier this way. Now, this is no longer called hydrogen, the element hydrogen, or an atom of hydrogen. This is now called hydrogen gas. H2 is the way we define that. Oxygen does the same thing. Oxygen is called O2 when one oxygen atom and another oxygen atom get together, except they share two pair of electrons. And so we call that a double bond. And nitrogen can share three pair of electrons, and that's called a triple bond. So this is commonly how you see these are gases in the natural world, right? You see hydrogen gas, you see oxygen gas, H2, O2, N2. You are surrounded by N2 right now. It's all over the place. Right, so covalent bonds are very, very common throughout the world of physiology, all over the place. So here's methane, here's carbon dioxide, CO2, and so these chemical formulas relate to, you can tell there's one carbon and there's four hydrogens, right? Here carbon dioxide has one carbon and two oxygens. Great. Ethanol over here has two carbons, five hydrogens, and one OH group. That's what makes it an alcohol, the OH group. We'll get into that later. These are just different ways that covalent bonds can be made. Now, here's how we draw them. This is where you're going to see when we start really getting into metabolism. How do you get energy? What you're going to see is you're not going to see these kinds of representations. We're not going to draw these pretty pictures out with all these colors, right? It takes too long. Easier way to do it is just to draw, like if they're combined together into kind of a hexagon, and we just draw it like that. If they're combined together into this long chain, we draw them this way. We draw them in the easiest way possible. Now in chemistry, anytime you see an angle, right? So a line joins with another line at an angle. At that point, that's a carbon. We know it's a carbon. All right. Here's a carbon that's double bonded to another carbon. How do I know that? Because it's drawn that way. I know chemically what I'm looking at. So that's what you're going to see. You're going to see this is a shorthand. It just takes too damn long to draw all these things out every time you want to draw one out. So then we start drawing them out like that. Okay. Hold on. Yes, so I want to get into, I'm going to go a little further with this. And in a second, I lost my menu. Yes, that's why I'm frantically looking around. I can't find the thing that I am trying to find. Oh dear. Where to go? All right, I found my menus finally. So what this leads us to, so we have covalent bonds, right? Two atoms could share a pair of electrons, and they could share them evenly, equally, and both be happy. And that'd be great. That'd be great. That would be called a non-polar covalent bond. If, on the other hand, you have two atoms that are sharing a pair of electrons, but one of them is really big and has a lot of protons in its nucleus, and the other one is really small and only has a few protons, or maybe just one proton in its nucleus, it's going to have the less of ability to pull on that electron. Yes, they're sharing the electron, but the big atom has more pull on that electron, just simply because it has a bunch more protons. It has more positive charge in the nucleus than the other one. So it's going to pull harder on that electron. If it pulls harder on the electron, it pulls the electron toward it, but it also pulls it away from the other atom. If it does that, we call that a polar covalent bond. It's still covalent. They're still sharing the electron, but it's now polarized in a manner of speaking. So that electron has a negative charge, right? If it's pulled toward the bigger atom, that atom has a little bit more of a negative charge than the other smaller atom. So we would say that that atom, that end of the atom, has a slightly more negative charge than the other side of the atom, which has a slightly more positive charge. This is the essence of water. I am describing water. We'll get to that in a moment, but I'm telling you, this is why water is the coolest thing ever. Right, so if they share that electron exactly evenly, we say that's a nonpolar covalent bond. If it has some polarity to it, that is described as electronegativity. It doesn't matter whether you understand the concept of electronegativity. The big idea here is that one of those atoms pulls a little harder because it can on the electron on the electron pair that it is sharing with that other atom. That's called a polar covalent bond. This concept really matters in physiology. Right, so summarize here. Covalent bonds can be polar or nonpolar. Nonpolar molecules contain nonpolar covalent bonds. Okay, oxygen, oxygen, they're the same size. They're pulling on the electrons that they're sharing with the same degree of veracity. They're grabbing and pulling, but they're pulling evenly. So we consider that nonpolar. Right, so it says here, right, an oxygen and an oxygen. Now it turns out that carbon and hydrogen are also nonpolar. They pull about evenly. Even though carbon is bigger than hydrogen, it turns out that they share the pair of electrons that they're sharing. They share it about evenly. So that's considered a nonpolar bond. A polar bond between like an oxygen and hydrogen, oxygen is much bigger, pulls harder on that pair of electrons. So that makes oxygen a little bit more negative, and it makes the hydrogen a little bit more positive. Slightly, tiny, not quite to the ionic level. But it's polar, it's polarized, we say. Now, nonpolar molecules can contain polar covalent bonds if the polar covalent bonds cancel each other out. What the heck did I just say? Let me show you. Carbon dioxide is a good example. I hope it shows a picture. Now let me go back to carbon dioxide. Here is carbon dioxide, okay? Carbon in the middle, oxygen on the outside there, oxygen on the other side there. They're in a straight line. Carbon does not pull as hard on the electron pairs as oxygen does, but this oxygen pulls on those electron pairs, this oxygen pulls on those electron pairs. They pull in a straight line. They pull as hard as each other. And so this is a non-polar molecule. Even though you'd say, well, wait, these bonds are polar. Yes, but they're on opposite ends, and you have the same bond on each end. So this is a tug of war where the teams are even. The oxygen and the oxygen are pulling on the carbon, and they're pulling exactly the same on that carbon. Non-polar. In a similar way, I'm going to go back up another slide here. In a similar way, this oxygen and that oxygen sharing two pair of electrons. They are pulling on those pair of electrons, the two pair of electrons, exactly the same. Non-polar. Just I bring up oxygen and I bring up carbon dioxide specifically because you're going to need to understand that these are nonpolar bonds because of how they behave physiologically. They behave physiologically like nonpolar substances, and that's extremely important for their physiology. All right. Now, I just said covalent bonds can be polar or nonpolar, right? Now, there's another kind of molecule where you can have really big, long molecules, where at one end of the molecule you could have some polarity, and at the other end you have nonpolar bonds. So you could have polar bonds at one end and nonpolar bonds at the other end. These are referred to as amphipathic molecules. You'd say, oh God, he's going on into chemistry too long. Oh, I'm never going to get this. Let me show you something. Again, amphipathic molecules are unbelievably important for making cell membranes, and cell membranes are life. You'll see when we get to that. So, cell membranes are made of these things called phospholipids. Let me show you. I think there should be, yeah. So, this is just a picture of it, right? These are a bunch of carbon and hydrogen bonds. On one end, these are all nonpolar, 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 nonpolar. At the other end, there's this thing called glycerol, which has some polarity to it. Or, well, I'm sorry. This glycerol. If you add onto the glycerol, if you add on what's called a phosphate group, then it becomes a polar bond or a polar molecule. So this molecule is nonpolar. I'm sorry, I didn't mean to confuse you. This molecule is a polar molecule. This molecule is found inside of cell membranes. And cell membranes have a polar end of the molecule and then a nonpolar end of the molecule. And we're going to see when we get to cell membranes, you'll see why this is important. All right. So we have nonpolar covalent bonds, we have polar covalent bonds, and we have amphipathic molecules that have both of these, polar and nonpolar, at opposite ends. I know you're thoroughly confused. Hang on. So we've talked about two bonds so far. Ionic bonds, where electrons move from one atom to another atom. They're given up. We have covalent bonds. Covalent bonds can be polar or nonpolar, but either way, they're sharing a pair, at least one pair of electrons. So ionics, give them up. Covalents, share them. Third kind of bond that you need to understand. The third kind of bond is what's called a hydrogen bond. A hydrogen bond is a very weak bond, but it's because there's a slight attraction between bits of one molecule and a bit of another molecule. There's a very, very slight, very weak attraction. We refer to that as a hydrogen bond or hydrogen attraction. They're also extremely important in biology and physiology. They're weak enough that they can be pulled apart when you want to pull them apart, but they're strong enough to stay together when you want them to stay together. So I know that doesn't make much sense now, but it will make much more sense. When you think of a hydrogen bond, DNA is your classic example. DNA has, well, we'll get to the chemistry of DNA in a bit, but you have a big long strand of DNA on one side, a big long strand of DNA on the other side, and each of those strands bonds to the other strand through hydrogen bonding and holds it together. That's called the double helix. You've heard of the double helix. The double helix is held together by hydrogen bonds. One hydrogen bond is pathetically weak, two is a little bit stronger, but when you put 1,000 of them, or 10,000, or 1,000,000, which is what DNA does, then they're pretty strong. They're strong enough to hold together. but not so strong that you can't pull them apart. So this is an example of hydrogen bonding, right? Hydrogen bonding is between very weakly polarized ends of molecules. So this is an example of, now this is a model of water. Right, here's a model of water, here's water, here's water. Now this is a sugar called glucose. Now in this particular case they have drawn out for you the carbon and the carbon and the carbon and the carbon, carbon and the oxygen, and how they all fit together into kind of this ring structure. But glucose is very soluble in water, right? We would say that it dissolves in water very easily. Sugar, right? Why does it dissolve in water? Because it forms hydrogen bonds with the water. And so water turns out to be a very good solvent. Solvents dissolve other molecules. The other molecule that is dissolved in the water is called a solute. So a solvent is the thing doing the dissolving. The solute is the thing that's in there, dissolved. Dissolved means, in this case, in the case of water, dissolved means it forms hydrogen bonds with that molecule. That's how it stays dissolved. All right, now we're going to talk about water. All right, water. Water, I've been telling you as we've been going along, water. Very, very important. Water is extremely, absolutely necessary for us to describe how life works. So we look for water. Why is water so great? Water has covalent bonds. So what's water? Water is H2O, right? But you have an O here, and an H over here, and an H over here. But you notice that they're not in a straight line. So remember, carbon dioxide was a straight line, so it's nonpolar. Water, you tip those angles, or those bonds with the hydrogens up at a little bit of an angle. You also have the idea that oxygen is much bigger and can pull much harder on those shared electron pairs. So you have an electron pair between this hydrogen and that oxygen, and this hydrogen and that oxygen. And that gives you what we refer to as an electronegativity difference. What does that mean? That just simply means that this end of water has a very, very slight positive charge, and this end of the water has a very, very slight negative charge. That means that these hydrogens can interact because they're slightly positively charged. They will interact with things that have a slight or a big negative charge. Right? So the negative and positive of something. So when you take table salt, which has sodium chloride in it, sodium is positive, chloride is negative. You put it in water, the chlorides start to hydrogen bond with this end of the water molecule. And the sodium, which has a positive charge, interacts with this end of the water molecule. What that means is, what you get is salt dissolves in water. Now you saw what happens when you put solid sodium in water. When you put sodium chloride in water, it just dissolves. And then it tastes good. Well, depending on how much you put in, but yes, this is why. Water has this very, very special property that it is slightly polar, and so it can dissolve things that have a slight polarity to them. The other thing to think about, the other thing that you have to also understand is when you try to dissolve something that is nonpolar in water, it does not dissolve. Why not? Well, you know the adage, right? Oil and water don't mix. Oil, like olive oil or castor oil or name your oil, vegetable oil. Any kind of oil is a nonpolar substance. Water is a slightly polar substance. So you put them together, they don't mix. So we've, you know the adage, of course. Oil and water don't mix. Well, they don't mix for this reason. All right. Water, you already know this part. Water can be a gas, it can be a liquid, it can be a solid. The beauty of water, too, is that it's a gas or a liquid or a solid at temperatures pretty close to temperatures that we can tolerate, that we can handle. It turns into a gas, that's maybe not so great for you. But liquid and ice, that's okay. You can survive that. But it can occur in these three phases. Now, water, because of these properties, does all of this stuff. It transports, it lubricates, it cushions, it excretes wastes. It's the fluid that does it all in physiology. It has cohesion. Cohesion means because it's attracted to itself. Because water, all by itself, has a slightly positive end and a slightly negative end, but the next water molecule over has the same thing, and so they will orient themselves so that they're all attracted to each other. That causes what we call cohesion. They like to stick together. That's why it creates this thing called surface tension, because they kind of stick together. You've seen insects that can crawl around on water, like water striders. They can do that because water has surface tension, and that surface tension allows a water strider to sit on top of the water instead of sinking into the water. So water has these weird properties to it that make it physiologically extraordinarily valuable. Universal solvent, right? It dissolves almost everything. Almost. Can't dissolve things that are nonpolar, but other than that, it can dissolve almost anything else. Right, so we already talked about this. Things that dissolve in water: polar molecules and ions. Right? So things that are hydrophilic love water. Salt is hydrophilic. It loves water. So if salt dissolves in water, the sodium goes one way, the chloride goes the other way. They separate from each other. They're no longer attracted to each other. The water molecule surrounds it surrounds the sodium and it surrounds the chloride. And in that particular case, we say it forms a hydration shell. That's not important. So the sodium and the chloride are no longer sodium chloride. They're sodium and chloride. So they act differently now. They act independently. But not all molecules do that. Right? If you dissolve glucose or any sugar in water, it stays as glucose. It's a solid glucose in your sugar bowl, if you have a sugar bowl, and you dump it in water and you spin it around and then it dissolves, and yet it's still glucose in there. It still has the molecular properties of glucose. Alcohol does the same thing. But like I said here, right, substances dissolve and dissociate. NaCl separates into separate sodium and chloride. Acids and bases also separate into, in the case of like hydrogen chloride, which is hydrochloric acid, hydrogen and chloride separate from each other. So water's the big thing. Even amphipathic molecules that have polar and nonpolar regions. Now the polar regions will interact with the water, but the nonpolar regions won't interact with the water. So that gives them some really interesting properties. And we're going to talk about that when we get to cell membranes, because it's an extremely important idea in cell membranes. We'll get to that. See, membranes of a cell. We'll talk about that. And then this is a picture of what we were just talking about. Right? So you dissolve glucose in there. Glucose is still glucose. This molecule of glucose still stays together. It's just dissolved. Right? But sodium chloride gets dissolved. Sodium gets surrounded by water facing one way. Chloride gets surrounded by water molecules facing the other way. But it's still dissolved. Now this term hydrophilic means it loves water. It means whatever you mix with the water, it's going to mix, and it mixes up really well. If it doesn't mix with the water, then it's called a hydrophobic. A phobia. A phobia is a fear, right? So if this thing doesn't like water, it's afraid of water. It's hydrophobic. Oil and water, they don't mix. But there are situations where you have to mix oil and water in the body, especially in the gastrointestinal system. There are ways to do that, right? If you've baked anything, you know that you put oil in certain recipes, but you also have water in those recipes. Well, oil and water don't mix. So you put something else in there that helps them to mix together, right? That something else is usually called an emulsifier. An emulsifier will get oil and water to play nice. It doesn't get them to mix perfectly, but it gets them together better. We're going to talk about emulsifiers. And that's what they're talking about down here. If you're going to get oil and water to mix, you have to add an emulsifier. And there's biologic emulsifiers in baking. Usually lecithin is the thing that you would use to join things that have oil and water, and you need them to mix together. All right, that's it. I'm saving acids and bases for the next video. I'm stopping here with this one, and I will add acids and bases and other stuff to the next video. Thank you for your attention. Have yourself a good day. I'm going to go about the process of figuring out how to get these videos online, which I'm slowly doing.